In agentic systems, efficiency is engineered, not hoped for. Caching avoids repeated work, batching smooths demand, and rate controls keep consumption inside guardrails. Together, these levers reduce cost, protect reliability, and prepare agents to operate at scale. We've moved from why agentic AI costs behave differently, to measuring quality and value, to making work visible through observability. Now optimization becomes practical. Reduce repeated work, handle bursty demand, and set guardrails that keep consumption efficient without weakening outcomes. As AI workloads grow, not every request should go straight to the most expensive service. An optimization control layer acts as a demand manager. Caching answers repeated questions with safe, reusable results. Batching holds non-urgent work briefly, then processes it together for better throughput and lower unit cost. Rate controls enforce quotas, throttles, and budgets, so spikes or loops cannot drain resources. The key is governance, not blunt blocking. Policies and observability determine what can be reused, delayed, or limited while protecting freshness, security, and the user experience. Prompt response caching stops you from paying the model for work you have already done. When a request arrives, the system builds a cache key from details, such as the prompt, model version, system instructions, temperature, retrieval context, and tenant scope. If there is a match, it returns the stored answer immediately. If not, it calls the LLM, validates the result, attaches metadata, and stores it with an expiration time. This works best for repeatable tasks like FAQs, classification, extraction, and standard summaries. Use extra care with sensitive, personal, or time-sensitive outputs. Semantic caching goes beyond. Have I seen this exact prompt before? It asks, have I already answered this intent? That makes it useful for support, policy lookup, and recurring analysis, where users phrase the same need in different ways. The trade-off is risk. A loose similarity threshold saves more cost, but can return the wrong answer. A strict threshold is safer, but misses reuse opportunities. So semantic cache hits need boundaries: tenant, permissions, domain, language, and current context. For high-risk tasks, add confidence checks, validation, or human review before serving the cached response. Embeddings can also be treated as reusable artifacts. During ingestion, only embed a document chunk when the source text, chunking logic, pre-processing, language, and embedding model version do not match an existing cache entry. For queries, cache repeated normalized queries to avoid paying the embedding cost on every search. The cache key must include version tags, such as model v3, chunker v2, and source hash, so stale vectors are not reused. When content, model, or normalization changes, invalidate and recompute. Retrieval caching helps because many users ask similar questions, and the system often repeats the same expensive steps. Instead of embedding, searching, filtering, re-ranking, and assembling context every time, reuse earlier results at selected checkpoints. The cache might store raw document matches, a re-ranked set, or the final context window passed to the model. The hard part is validity. Results can become unsafe or wrong when documents change. Permissions shift, filters differ, or ranking models are updated. Track hit rate, stale results, latency saved, and whether answer quality actually improves. Tool result caching is valuable because agents often repeat expensive calls to APIs, databases, crawlers, calculators, or business systems. The safe rule is to cache only when the result is stable enough, permission safe, and clearly scoped. Good candidates include product metadata, policy documents, deterministic calculations, or exchange rates within a defined window. Build cache keys from the tool name, parameters, authorization scope, data version, and environment. For volatile data like pricing, inventory, account status, or security posture, use short TTLs or event invalidation. Never share cached results across users or tenants without enforced isolation. Good cache governance starts with deciding when reuse is allowed. Each cache needs a TTL, invalidation rule, scope, and sensitivity classification. Then monitor whether caching is actually helping. Hit rate, miss rate, evictions, stale responses, latency saved, cost avoided, and quality regression. The point is not to optimize blindly. For regulated, personalized, high-risk, or real-time decisions, bypass the cache and compute fresh results. In AI systems, cache behavior is part of quality control and compliance, not just an engineering shortcut for speed or cost savings. Not every AI task belongs in the user's waiting time. If a job can finish later, move it into a queue and let workers process it independently. This pattern fits document processing, model evaluations, enrichment, and scheduled summaries. The queue smooths spikes in demand, supports priorities, and gives you a place to apply retries and backpressure. Workers can call models and tools in batches, often reducing overhead and cost. The operational discipline matters. Track status, handle failures, make jobs idempotent, and keep users informed with clear notifications. Consider a support platform that enriches every ticket the moment it arrives. That sounds helpful, but it can add latency and cost to the user-facing workflow. A better pattern is hourly batch enrichment. Classify tickets, summarize history, update CRM fields, and retry failures together. The same idea applies to evaluations, document pipelines, daily summaries, and back-office queues. If the work matters but can wait, batching often makes it cheaper and more reliable. Reliable batch pipelines are built around one assumption: something will fail. Jobs should be idempotent, so rerunning them never creates duplicate records, charges, or notifications. Retry logic needs clear rules. Back off when systems are overloaded, separate permanent failures from temporary ones, and move unresolved work into a dead-letter queue for inspection. Since not every job deserves equal treatment, prioritize by business value, deadline, user impact, and available budget. Finally, monitor the pipeline like a product. Throughput, queue depth, oldest job age, failure rate, cost, and output quality should all trigger alerts before customers notice. Agentic systems need consumption controls because autonomy can multiply usage quickly. Quotas answer: how much is allowed over a period? For example, tokens per day or dollars per month. Rate limits answer: how fast can requests arrive? They smooth spikes and avoid provider throttling or overload. Budgets answer: how much money can this system spend before intervention? They should trigger alerts, approvals, throttling, or shutdown. The key is layering. Apply controls per user, agent, team, application, and environment, so one runaway workflow cannot exhaust shared capacity or surprise the business with unexpected cost. Rate controls should behave like an automated policy engine, not a hard stop. When a request arrives, first check current quota and budget health. If everything is healthy, run normally. If spend is approaching a threshold, optimize. Switch to a cheaper model, shrink context, reduce retrieval depth, or defer non-urgent jobs. If limits are exceeded, apply priority rules. Production and critical workflows get protected, while development, testing, and low-value experiments are throttled. Then tell users what happened, when to retry, what was reduced, and how to escalate. The core pattern is simple: reuse, defer, and govern. Cache work that should not be repeated. Batch or run asynchronously when speed is not the priority. Then use quotas, rate limits, and budgets to keep consumption predictable. Next, we connect these FinOps controls to agent design choices: planning loops, tool use, task decomposition, and execution strategy.